Okay, everybody, hi. We're going to now wrap up this chapter on multiple integrals, looking at another type of coordinate space, spherical coordinate space. So this is going to be useful when the area of integration, this volume of integration, is spherical in nature somehow. So in spherical coordinates, a point P in space is going to be determined by three values: rho, theta, and phi. So if you were to have this point in 3D space, if you were to look at the distance from that point to the origin, this distance is a distance of rho. If you if you take this point, go down, project it to the xy plane, this angle between the x-axis and this point, the kind of the line containing that point, that's your theta. And then if you were to look at the angle between that, if you draw a straight line to this and then you're looking at the z-axis, this angle is phi. So these are the three angles or the three kind of values that determine the position in 3D space. So you can see that the theta can range from anywhere from 0 to 2 pi. Phi, on the other hand, is going to go from 0 to pi. So if you have a value of phi that's greater than pi over 2, then you're going to be down below the xy plane. And so then we have a few conversions that we can use to convert from rectangular to spherical coordinate space. X would be rho times the sine of phi times the cosine theta. Y is rho times sine phi times the sine of theta, and z is rho times the cosine of phi. And then rho squared, which is kind of like what r squared was back in cylindrical or polar coordinates. That would just be x squared plus y squared plus z squared. This is how you can get from rectangular to spherical and vice versa. Okay. So if you wanted to express the coordinate 2, pi over 4, pi over 3 in rectangular coordinates, we said that you can think of it. So this is rectangular coordinates. X, as we said, it's rho times the sine of phi times the cosine of theta. Now here we have our rho, we have our theta, and we have our phi. All right, so here rho is 2. The sine of phi, that's the sine of pi over 3. And then we have the cosine of pi over 4. Now remember, pi over 3, in the unit circle, pi over 3 is right up here. That's dividing pi. The sine is root 3 over 2, and that's 1/2 for the cosine. So this is going to be 2 times root 3 over 2 times root 2 over 2. So that comes out to be root 6 over 2. Y is rho times the sine of phi times the sine of theta. So this is going to be 2 times this root 3 over 2 times another root 2 over 2, because the cosine and the sine of pi over 4 is the same thing. So it's going to be the same thing, root 6 over 2. And then z is going to be, it's just rho times the cosine of phi. And so that's going to be 2 times the 1/2. That's the cosine of pi over 3. And so that comes out to be 1. So in rectangular coordinates, the point is root 6 over 2, root 6 over 2, and 1. And then just as another conversion, let's convert this coordinate point to spherical coordinates. So we have the point. It may be useful to just try to sketch it a little bit to see if we can figure out where this thing is. The x value is 0. The y value is 2 root 3 over 2. So that's 2 root 3. Sorry, 2 root 3 is whatever that is. It's going to be about a little less than 4-ish. So I'm going to put it, this is the point. Now, as far as the, because this is, if you look straight down with the y and the x, this point is right here. The theta is going to be pi over 2. That's the if you go to the z-axis and you go around to the x-axis, that's pi over 4, or sorry, pi over 2 radians, right? That's right directly like underneath that y-axis. As far as the z goes, we have to kind of come up with a triangle here. Figure out what is this. This, I should put it on the other side. This is the phi, right? And so, in terms of the phi, probably the simplest one to start with is to get rho. You know, as I said, rho squared is x squared plus y squared plus z squared, right? So rho squared in this case is 0 plus 4 times 3 is 12. That's y squared plus a 4. That comes out to be 16. So that means rho is going to be 4. And as we had before, the since you know that z is equal to the cosine of phi, it's rho times the cosine of phi. We actually can write -2 is equal to 4 times cosine phi. So cosine of phi is equal to -1/2. That leads us to, we can solve for phi is going to be 2 pi over 3. And because we've got, you can take the other one, say x, for example, is equal to, x is rho times the sine of phi times the cosine of theta. Well, we have 0 equals 4 times the sine of phi is going to be the sine of 2 pi over 3. That's root 3 over 2 times the cosine of theta. In this case, well, you can see this just gets us to the exact same place. This theta has to be equal to pi over 2. That's the angle whose cosine is 0. So what we get then for our point in spherical coordinates would be 4 pi over 2 and then 2 pi over 3. Okay, so let us think about how we are going to convert what was before dv, these little rectangular boxes in 3D space in rectangular coordinates, to little tiny chunks in spherical coordinates. And so what we're going to do is look at dividing it and approximating it into these little things based on their 3 dimensions, and the dimensions are going to be the like this dimension here, then we have this dimension here, and then we'll have this dimension here. So the product of those 3 dimension lengths is going to give us the value of dv. So the first one is straightforward. The distance between the inner layer of the inner boundary of this layer and the outer boundary is just like a change in rho. So delta rho is like the first piece of this thing. The second piece of it is, as you remember, phi is how your has your changing this angle from the z-axis. A little change in phi is going to be this next component, but the thing is, so this is giving you the length here, and as you can see, that length is going to depend on how far we are from the origin. So it's actually, that's going to be rho times delta phi. So it's going, this length is going to be scaled linearly with how far away from the origin point we are at. Now the third one is probably the trickiest one to think about. It's this little length there, and what we want to do is, we're of course we're looking at a change in delta, or a change in theta, but we're interested in knowing how far away, like what is the distance. If we project this point straight down to the if we project straight down to the xy plane, where are we at? And if you remember, that x is rho times the sine of phi times the cosine theta, and y is rho times the sine of phi times the sine of theta. Rho times the sine of phi is this length. So if you project the point straight down onto the xy plane, what you get is you're at the point rho sine phi, distance away from the origin. So these little delta thetas is scaled linearly with that length. That's rho sine phi. So we have rho sine phi and then delta theta. So altogether then our dv becomes, we collect all these terms. We have rho squared sine phi, and then we have d rho d phi d theta. This is what our differential volume is in spherical coordinates. Now, I don't expect you to memorize the derivation of this, but you do need to know when you convert to spherical coordinates, you get a rho squared and you get a sine phi, and you can't get away from that. Those are just part of it. You can't not have those there. Okay, so let's integrate this function e to the x squared plus y squared plus z squared to the 3/2 power dv, where the region of integration is a unit ball. So this is a unit ball which has a radius of 1, so it's going to be right. It's going to kind of intersect there. So come around, and we've got this unit ball, so it has a length of 1. Now, when we are setting up this integral, we're going to set up first theta is going to go from 0 to 2 pi, because we're going to be going around the whole thing, rotating around all around the xy plane. In terms of phi, however, we're going to be going from up here and swooping down to there, down to the negative z-axis. So that's going to be going from 0 to pi. And as far as the radius goes, or rho, the distance from the origin, that'll go from 0 to 1. Now, remember that the conversion here, right, is rho squared is x squared plus y squared plus z squared. We gave that a little earlier. That's going to be important here. So e to the x squared plus y squared plus z squared is, to the 3/2. That's e to the rho squared to the 3/2. So that's actually e to the rho cubed. So we have e to the rho cubed, and then what do we have? We have rho squared, we have sine phi, and then we have d rho, d phi, d theta. Now here we're actually able to do this integral because we happen to have this rho squared there. Let's do a little conversion of units. I'm going to let u be rho cubed, and so du is going to be 3 rho squared d rho. I'm going to have to introduce a 3 here, but I have to put a 1/3 out front in order to keep things balanced. And my integral, well, because there's no theta, I can take care of the theta right away. So I can write 2 pi over 3, and I'm still going to go from 0 to pi. And my bounds on u are going to go from 0 still and 1, because 0 is 0 squared and 1 is 1 squared. But now I'm going to be integrating e to the u sine phi, and then du and d phi. So the phi is going to be taken care of next. And actually, I could have done that concurrently, but I'm not going to. I'm going to just take care of this one at a time from here on out. 0 to 2, 0 to pi. It's just e to the u from 0 to 1, sine phi d phi. So it's 2 pi over 3. We're going to have integral from 0 to pi. I'll write the sine phi here, d phi, and just evaluate this. We've got e minus 1. That's e to the 1 minus e to the 0. And the integral of, so 2 pi over 3 times e minus 1, the integral of sine phi from 0 to pi is going to be, comes out to be 2. Because as you know, if you take the sine function from 0 to 1 to 0 to pi, 2 pi, there's an area of 2 in here, this negative 2 down there. That's a little shortcut that's useful, knowing about the area under the curve for the sine function. So anyway, that's 2, and so altogether we got 4 pi over 3 times e minus 1. Okay, so let's use spherical coordinates to find the volume of a solid lying above a cone, z equals x squared plus y squared, and below a sphere. This is going to look like this. It's going to look like a snow cone. So you have the, this is the, I'm going to just draw it on the z y plane. We've got this, this is the line z equals square root of y squared, and that would be like rotated around. All right, so this would be a cone going around. Now this is we're looking at the volume above that, but below a sphere. X squared plus y squared plus z squared equals z. Now this sphere, I'm going to actually write this as this is x squared plus well, actually let's see. Let's write this as x squared plus y squared plus z squared minus z equals 0. I want to complete the square. That's the thing. Actually, what I want to do is add 1/4 to this, and so I'm going to have 1/4 on the other side. This is a sphere with center 0, 0, 1/2, and a radius of 1/2. So this is going to kind of look like this is, if this is at 1/2, we're going to sort of have a spherical top like this. Okay, so now if you continued, it would come around to the origin. So what we need to do is to so it's clear that we need to how far out we're going, right? At all these cases is we're going out to this thing, but we're only as far as theta goes. Theta is going to be going from 0 to 2 pi, right? Because we're going to be going all around the z-axis back, right? So a full 2 pi around on the xy plane. As far as phi goes, we're going to be going up from 0, but only going down as far as this cone, which is a 45-degree angle. That's only going to be pi over 4. Right? Now, as far as rho goes, rho is going to be bounded between 0, of course, and this. Now, I'm going to have to convert this to polar coordinates. This equation here. Now, let's take this x squared plus y squared plus z squared equals z. This is actually rho squared equals z. Now, how do we convert z? Z was going to be rho times the cosine of phi. And so if I was to, let's see, I could factor, well, we know that rho is positive, so I could divide by it. This is the equation rho equals cosine of phi. So that's the upper bound of, that describes the surface of this snow cone thing, this upper surface, the cosine of phi. So our bounds on theta from 0 to 2 pi, our bounds on phi from 0 to pi over 4. Now the bounds on rho from 0 to cosine of phi. What are we integrating? We're integrating the sine. Oh, sorry. We're integrating rho squared sine phi d rho d phi d theta, right? To find the volume of this solid, we just integrate the value, the function 1, and then we have the dv. Now remember, dv comes with the rho squared and the sine phi. That's part of the package deal. So I'm going to integrate with respect to rho first. And actually, because there's no theta at all involved, I'm just going to put a 2 pi out here because that's going to be, in the end, you're just going to be multiplying by 2 pi. And so what we're going to have is integral of rho squared is going to be rho to the third, or the 1/3 out front. And we're going to be going from 0 to cosine of phi. We have a sine phi, and we have d phi left. Nice thing about this is just a matter of plugging in cosine phi in. So we're going to get 2 pi times integral from 0 to pi over 4. That's actually, I put the third under the 2 pi. And then we've got cosine cubed phi times the sine of phi, d phi. And the nice thing about this is, of course, that the derivative of the cosine is negative sine. So actually this is going to be, right, because the derivative of the cosine is the negative sine. We have a sine there, so if we did some sort of substitution, let's just do it because it'll keep things cleaner. I'll let u be the cosine of phi. du is going to be negative sine phi d phi. Right? So this isn't negative, so I'll have to make it negative, and I'll have to make this negative as well to make things equal. So we have negative 2 pi over 3. The bounds are going to be, the lower bound is going to be the cosine of 0, which is 1, and the cosine of pi over 4 is root 2 over 2. And then what we have is just u cubed du, right? So we have negative 2 pi over 3, and then we're going to have 1/4 u to the fourth from root 2 over 2, which might as well just write that as 1 over root 2, and then from 1 to that. Now, of course, we have 1 over root 2 is smaller than 1, so we could flip those over, but in the end, it's not going to make a, well, it, yeah, let's do that, actually. I'll make this thing positive, and I'll just change the bound so that I have 1 up top, and I have 1 over root 2 down below. What do we get when we evaluate this? We're going to have 2 pi over 3. Well, let's do it 2 pi over 12. Actually, let's just take the fourth out. We have, that's going to be pi over 6. And then we're going to have 1 minus, what's 1 over root 2 to the fourth? That's going to be 1 fourth. And so this is 3 fourths. So this is 3 pi over 24, which is just pi over 8. That's the volume of this snow cone. So let's see. I guess that pretty much does it for a couple examples. This is just something we'll do a little bit of practice in. There's certain applications where spherical coordinates are going to be easiest, but it's not going to be super prevalent. So you need to know about it so you can use it when you need it. But we're not going to have a ton of practice using this on homework. All right, I think that's it for now. I will see you in class. Bye.